Well, good evening, Miss students. This is Mr. Rich. It is Sunday night Q&A, 8 o'clock, and today is October 6th. I'm going to work through some Algebra 2, AP Precalc, and some AP Calc questions. I've got some AP Calc questions that came through. I'll get to those. As I did promise in the email that I sent out this weekend, I wanted to go and show you a certain feature in Desmos that I think will help everybody, and it is the topic of regression. One thing that I want to show you about Desmos is that if you have a set of ordered pairs and you know what the line of best fit or the graph of best fit would look like in terms of it being a line or a quadratic or maybe a third degree polynomial or even an exponential function, Desmos will do the regression analysis and find what we would call the line of best fit or the graph of best fit. And I want to show you really how you could just find an equation of a line if you know 2 points. For example, if I have 2 points, 12, 3, and negative 4, 5, and I wanted to find the equation of a straight line that passes through those 2 points, you all know, I assume, that y equals mx plus b is one equation that we could use, but we could also use point slope, right? Which looks like this: y minus y1 equals m times x minus x1. However, and of course, the process would be, let's find the slope of the line, that's our m, and then for x1 and y1, we could put in one of the coordinates into the equation, and then we would have the equation of the line. Well, in Desmos, let me show you what an option is. And this is something that you could do on the SAT even. So what I'm going to do in Desmos is you can put a table of values in Desmos. You can hit this plus right here and put in a table. And I'm going to put in the 2 ordered pairs. And the 2 ordered pairs are 12, 3. So we'll put in 12 and 3. And we'll put in the other one, which is negative 4 and 5. All right, so I got the table in there. And I want Desmos to find the line that would pass through those 2 points. And here's how we do it. I'm going to put y1, right? I don't want to put y, I need to put y1. If you hit y and the number 1 on your keyboard, it knows to make a subscript. So it automatically puts a subscript there to match the fact that we have a y1 in our table. I'm not going to put an equal sign, right? The secret to this is you have to know that Desmos is expecting a tilde. What is a tilde? Well, if I assume I'm saying that right, but if you click on ABC on their on that button here on the keyboard, this right here is a tilde. It's a squiggle. So you put that in there. And what that's telling Desmos is you want Desmos to run an algorithm to find the line of best fit. So what I'm going to do is I'm going to use the letter A and then x1. So A is going to be the slope plus B right there. And it's giving me the equation. It says that your slope would be negative 0.125. So I can write the equation here. Y is equal to negative 0.125 x plus b plus 4.5. And there it did. It did the work for me right there. And so let's see if that makes any sense. If we did calculate the slope manually, 5 minus 3, that's the rise, to negative 4 minus 12 is negative 16. Negative 4, take away 12, negative 16. So the slope is negative 1/8. And guess what? Well, negative 0.125 is negative 1/8. And then our y-intercept is 4.5. Here's another one that really might be something that you'd see in AP Precalc. Because in AP Precalc, those of you that are in that class in Unit 1, you know that Lesson 114 is having you do this sort of regression analysis on your TI-84. I'm not going to go into it on the TI-84 here, but I'm going to show you how it works in Desmos. This says that the function V gives the number of vehicles available for sale at a used car dealership. The table above gives values of V of t for selected values of t in days since the beginning of a particular month. A quartic regression. Okay, what in the world is a quartic regression? That's a 4th degree polynomial. Is used to model these data. What is the value of V of 28 predicted by the quartic function model? Well, what I'm going to do is I'm going to go to Desmos and I'm going to get rid of this table, get rid of that. I'm going to put in a new table. I'm going to put all the values of the days in. So we'll go 2, 8, 12, 19, and 24. And then we're going to come over here and put in the vehicles at each of these days: 65, 55, 44, 38, and 45. Well, a quartic regression, y1, that's going to be a fourth degree polynomial. So I'm going to put y1, put the tilde in, and I'm going to use different coefficients for each one of the terms of a quartic. So it would be ax to the fourth, ax1. See how it didn't like that? ax1 to the fourth plus bx1, that would have to be to the third power, plus cx1 raised to the second, plus dx1 raised to the first, plus e. There it is. So it's giving me the line of best fit right there. So I could write that equation down because that negative 0.006 is the coefficient that would go in front of the x to the fourth term. The b would be the coefficient for the x cubed, and so on. And then once you have that written down, you could then use that equation to make predictions for the number of vehicles for at a particular day. All right. So I just wanted to show you that you could use Desmos to do that sort of regression analysis by making a table. Any questions about that? Hopefully that's interesting. If not, well, we'll just move on to something else. I want to start off with a little bit of Algebra 2. And here's what I wanted to do in Algebra 2. Most of you that are in Algebra 2 are working in the quadratic equation module. And I wanted to go over problems involving quadratics that have a leading coefficient. See if I can find, yeah, this is it. I wanted to go over the method for factoring quadratics that have a leading coefficient that is not 1. Because one of the things that you will need to do is you will need to factor these. Factoring these is not something you have to do very often on the on an SAT or an ACT exam, but so it's not the biggest thing for that test, but certainly in your Algebra 2, we need to know how to factor those. There is a trial and error way that you can do it, but I want to show you a formal way that will work every time, provided it is one that can be factored. So it's called the AC method, and the AC method is this: you take the A, which is the 3, and you take the C, which is the -5, right? Because I'm talking about ax squared plus bx plus c, right? That's the standard equation for a quadratic. And you are going to multiply those two numbers together, which is -15 in this case. And then you're going to ask a similar riddle that you would have asked if there was a coefficient of 1 in front of that x squared, or p squared in this case. And that was the multiplication addition riddle. We're trying to find two numbers that would such that they multiply to be that -15, but they add to be the middle coefficient of -2. And if you think about that, those two numbers are going to be -5 and +3. Their product is -15. Their sum is -2. What I'm going to do is I'm going to rewrite our quadratic by replacing the -2p middle term with those two terms using the smallest one first. So it becomes -5p plus 3p minus 5. Well, why did we do that? Well, we did that because we're going to employ something called factoring by grouping. So I'm going to take these first two terms here and factor out their greatest common factor, which happens to be just a p. So when I factor that p out, I get 3p minus 5. There is no greatest common factor here, so I'll just factor out a 1. 3p minus 5. And what happens in this method is you'll notice that you get a common parentheses, a common factor between these two terms. And that becomes one of the factors that we're looking for, 3p minus 5. Well, when you factor the 3p minus 5, that leaves you a p plus 1 in this case, and we just completed the factorization right there. It's called the AC method. There's all sorts of tricky ways that teachers teach you, like they call it the slip and slide method or the borrow payback method. Those are, those are okay, I guess, but they can get you into trouble. You really want to know how to do this the right way, and that is this way right here that I'm showing you. It is worth figuring that out. Well, let's do one more of these. Let's see. Let's try. The numbers can get pretty big. I want to keep this simple. Let's go with this one here. Now, I'll show you. I could do this by trial and error, right? In this case, I would probably do this myself, trial and error, because I know the 2v squared ends up being 2v and v, and I don't have many options for the product here of 5 that would be placed in here. So it's if I put a +5 and a +1, I check my outer product 10v and my inner product 1v. That makes 11v, so I know that I nailed it. That's it. I got it. Now, if I was to use the AC method, I would do this. I would say, okay, 2 times 5 is 10. Two numbers that multiply to be 10 but add to be 11, sure, that's 10 and 1. So I would rewrite this as 2v squared plus 1v plus 10v plus 5. I factor out a v common factor from the first pair of terms, factor out a 5 from the second one, and sure enough, I have a matching 2v plus 1. And when I pull the 2v plus 1 out, I get v plus 5. All right, so that's the method that I wanted to show you there. Any Algebra 2 questions out there, students? While I'm on Algebra 2 on quadratics, you'll probably be in this unit for a couple of weeks. With this storm coming, who knows, maybe 3 more weeks. You never know. No questions? Algebra 2? Let's move on. What did I have for AP Precalc? Yeah, a lot of you that are in AP Precalc, I think there are a few of you here tonight that are taking AP Precalc. You have your summative this week, the last summative of Unit 1. And I thought there were a few problems I really thought would be good ones to work on. Let me see if I can find them. Yeah, the horizontal dilations. I did want to talk about that. Let's see. Where are they? I'm looking in chat. I don't see any questions coming in. Let me go back up here. I'll go over the graphical transformations problems here. Let's take a look at number 14. This comes from lesson. This is lesson 112. No, this would be lesson 113. Or no, 112. 112b is what I was thinking. But look at this. This function that they're giving us is f of x. They're showing us the graph of f of x. That's what it says. It says the graph of f of x is shown in the figure above. No, we're working this one. Okay, that's kind of weird. But yeah, this right here, the figure above consists of 3 line segments. It's called f of x, but then they create a new function h of x, which is a transformed version of f of x. And that's what it is right there. But then we have to know, what does it mean when you replace the x with 2x? Well, that means a horizontal dilation. When you replace x with 2x, it's what we call a horizontal dilation by a factor of 1/2, right? So whatever that multiplier is, its reciprocal is the dilation factor. Well, what does it mean to dilate a function horizontally? What it means very precisely is this. All the distances on the graph from the y-axis are going to be cut in half. We're basically going to take the function and we're going to squeeze it and make every single point half as far from the y-axis. And then we're also, this -3 means we would shift it down by 3. Shift down 3. So here's what I'm going to do. I'm going to take these points, 1, 2, 3, 4, and I'm going to apply the transformation to those points. So it would look like this. I'm going to take this point, squeeze it in half as far from the y-axis. That puts it here at 1.5. And then I would go down 1, 2, 3. So there's the vertical shift of 3. This point gets squeezed in to be half as far. So it's going to go to a 1/2. And then I'm going to shift it down 1, 2, 3. It's going to end up right there. So that line, this line right here is now that line. This point will get compressed to be half as far from the y-axis and then down 1, 2, 3. So that line now is right there. This point, which is at 1, 2, 3, 4, 5, it's going to get cut in half to put it at 2.5, and then down 1, 2, 3. Okay, so I took that function right there, compressed it to be half as far from the y-axis or half as wide, and then moved it down 3 units. That is Precalc. Any of you Precalc students got questions? I'm just seeing calc questions come in from Alexandria. Okay. Well, I will move over to calculus, I think, unless there's one other one I wanted to show here. Yeah, I think I did want to cover one more thing. When it comes to transformations of functions, right, you could expect to see questions on your summative that involve how the vertical or horizontal asymptotes might change when you are transforming the function. And I think there was another one that might be a little bit better. Let's see, or maybe it was up here higher. Yeah, let's take a look at number 30. They tell you that the graph of f of x has a vertical asymptote at -2 and a horizontal at y equals 3. And then it says, find the vertical and horizontal asymptotes of the following functions, which are all transformed versions. All right, can you hear me? Can someone type in the chat that you can hear me? Good. Oh my gosh, I can't believe that it kept everybody in here. All right, let me get back to it. I think my internet glitched. Let's get back to what I was saying here. Okay, so here we go. -3 times f of x over 5 plus 4 is how I'm going to rewrite that, just changing the order there. So I know that there were 4 things that were done. We had a horizontal dilation by a factor of 5 because it's x over 5. So that means the dilation would be the reciprocal. So it was everything was made 5 times as far apart. The negative that's in front is going to be reflection across the x-axis. The 3 is going to be a vertical stretch by a factor of 3. So we have a vertical dilation by a factor of 3. The plus 4 is a vertical shift, right? So it's a vertical shift up 4, and then we're reflecting it across the x-axis like that. Well, let's talk about, there's only one thing here that's going to affect a vertical asymptote, and that's going to be this horizontal dilation. All of these other things, taking a function and stretching it, I think Alexandria is trying to get back in. So, but to take a function and stretch it vertically is not going to affect the vertical asymptote. To vertically dilate or to stretch is not going to affect a vertical asymptote either, and neither will shifting it up by 4 units. The only thing that will affect my vertical asymptote is the fact that everything has to get 5 times as far away. So where is the vertical asymptote? The vertical asymptote, it says, is at x equals -2. So that means that my new vertical asymptote for h of x, it will have a vertical asymptote at x equals -10, because it's got to get 5 times as far away from the y-axis because of the fact that x was replaced with x over 5. Now, all 3 of the other transformations have to do with vertical, and so that's going to affect a horizontal asymptote. So if you have a horizontal asymptote setting here at y equals 3, and then you apply these transformations, let's do it this way, right? If I flip it around the x-axis, that's what the negative is going to do. It comes down to -3. Then I make it 3 times as far away, so that would put it down at -9. But then I'd be shifting it up by 4 units, so it ends up finally at y equals -5. So those are the kinds of things that you may have to do on your summative, is maybe relocate some asymptotes by knowing what the transformations were done. And your horizontal asymptote is only going to respond to those things that are going to be in the horizontal, right? Because vertical lines, moving them up and down or stretching them vertically, they're not going to change. They're still just going to be a vertical. But if you shift things left and right by a horizontal dilation or a horizontal shift, yeah, they're going to respond to that and they will move around. Next, we'll move on to calculus. Those of you that are calculus students, I did show this to the class I was just with last hour, this table of derivatives. If you don't have one of these, I recommend that you get one and keep it with you, or at least have it on your phone so that you could look at it. If you Google a table of basic derivatives, you will find this exact table. It should be the first Google hit that you find. But it has all of the rules and then some extras that we're not going to use in AP Calc AB. But it's got them all here, and it's got them all in chain rule form. So if you don't know what the chain rule is, then that doesn't make much sense. But you'll notice all of these are written as though they are the chain rule already applied to them. So it's a pretty cool thing. At the end of this, you'll see some rules that you already know. These are your exponential and logarithm derivative rules. There's some that we don't use, like the 6 hyperbolic rules and the inverse hyperbolic, but you see the quotient and product rules are here for you. And the nice thing about this table is it shows some examples. So that's one of the things I really like about this. If you can't find this, shoot me an email and I'd be happy to send it to you. Then at the end is a table of basic integrals. So when you get to the latter portion of this class, probably around December, January, you'll be studying antiderivatives. You'll be going backwards, starting with a derivative and then taking its antiderivative. And these rules will help you keep those straight. All right, let's do some questions that have come through. And again, if you've got any questions, you can slap a picture up there in our meeting chat, our Zoom chat, or you can send it to me at askmrrich@gmail.com, and that makes it really easy for me to grab it and bring it over. So I think this is going to work. Let's give it a shot. Because if you don't send me anything over, we're going to be working on problems that Alexandria has submitted. All right, Alexandria, this is the first thing you sent over to me. What number are we talking about here? Talking about number 2? I don't know. Let's see if Alexandria is still here with us. She is. Alexandria, yes. 2, 6, and 7. My goodness. I don't know. Let's see if we can tackle these. This says, number 2 says, which expression is equivalent to the inverse cotangent of x? Oh, that's a good question. The inverse function. Well, this is really not even a calculus question, is it? This is just wanting to know the inverse function of cotangent. Well, think about this. If we took y equals cotangent of x and we swapped the variables, that's how you find inverses. And then you decided to solve this for y, you would get y. Let's see, we'd have to take the inverse we would take the inverse cotangent. Yeah, so which one is is equivalent to that? I think that is a really good question because it's not asking us to take a derivative. So if we swap our variables and then solve for y, we would have to take the inverse cotangent of x, right? But that puts us back as to what that would be. So not sure. I'm eliminating, it's definitely not this, right? They're not saying, this notation does not mean to flip it, like raise to the -1. So that's not what it is. And could it be this? I really don't think that we can just take the inverse of cosine and sine on that. You know what, Alexandra, you have me stumped on this one for some reason. For some reason, my brain can't get around that one, but we'll come back to it maybe. Let's take a look at number 6. Number 6 is a calculus question. Find the domain of f prime if f of x equals the natural log of the natural log of x. All right, so for number 6, let's find f prime. So this requires us to use the chain rule. So to take the derivative of the natural log of something, what we do is we're going to put the argument down in the denominator and its derivative in the top. So the derivative of natural log of x is 1 over x. And then, but we also have to multiply by the derivative of the inside part, which is the derivative of natural log of x, which is 1 over x. So what happens here is that if we multiply this out, what we get is 1 over x squared times the natural log of x. And we're looking for the domain. So first of all, the domain of the natural log of x is x greater than 0. All right. And of course, we can't have 0 in our denominator here. So this has to be a x greater than 0. And then 7, find dy dx if y is equal to x raised to the e plus 1. Okay. What I would do to find dy dx is, no, e to the plus 1. See, e to the plus 1 is just a constant, right? Because e is a number, 2.718. So I'm going to use the power rule. So I have to take the e plus 1 to the front and multiply that times x to the e plus 1 minus 1, because I have to reduce the exponent by 1. So this ends up being answer B right here, right? E plus 1, the 1 minus 1 is e, so it's x plus 1 times x to the e power would be my answer on that one. Okay, any others? I know there were some of you who had emailed me and said that you had some questions in your math classes, but I just don't see the questions coming in. Make sure nothing came through the Ask Mr. Rich email. I'll pull up some more, maybe some more calculus questions. All right, here it looks like an inverse function problem. Question number 5 says, if g prime of 2, find g prime of 2, if g is the inverse of f and f of x equals negative 5x cubed plus 3x. Well, what I'm going to do here, I'm going to do this, I'm going to copy this thing over so we got some room to work with it. So let's move this over. You're seeing everything I have open here. I guess I don't have the one thing open that I want to have open. Let's go over back here. Yeah, let's do this. I'm going to grab this and move it over. There's our question and put it right here. All right, Alexandria, here is the question on derivatives of inverse functions. If I want to find the derivative of an inverse function, g being the inverse of f, and I want to do it at 2, I'm going to do 1 over f prime of g of 2. That's kind of the formula that we derive when we take the fact that compositions of inverse functions give you an answer of x. So we can derive this formula, but this is the formula for finding the derivative of an inverse function. So this means that I have to start with finding g of 2. And you may say, well, how am I going to find g of 2 if I don't have g of x? Well, because if f and g are inverse functions, if you're talking about a g of x and an f of x that are inverse functions, g of 2 is asking us to find the y value when x is 2 in the g of x function. But since they're inverses, that would mean that I'm really trying to find the x value when the y is 2 in the f of x, because whatever this number is here, it's going to be the same number here. So I am going to work with the f of x function. And I was working a problem similar to this in the prior AP Calc class last hour. And what we have to do is say, well, okay, if I need to find g of 2, I need to plug 2 in here for y and solve for x. And I'm not going to be using an algebra method. Strangely enough, I'm going to use trial and error. When I look at that equation, I think I need x to be a -1, because if x is a -1, x to the third would be a -1. -1 times 5 is 5. 5 plus 3 times -1 is 2. So the solution to that, without using algebra, but knowing that AP Calc, oftentimes that's what they do. They want you to solve that by trying a few numbers. X is -1. So that means that g of 2 is a -1, because I just found out that when y is 2 in f of x, the x value is -1. So that means that point must be on the inverse function g of x. So now I move to the next step. It's 1 over f prime of -1. Well, f prime is easy enough to find. I come back over here. That's going to be -15x squared plus 3. I can evaluate that at -1. F prime of -1 is -15. -1 squared is 1. -15 times 1, -15 plus 3, it's -12. So my final answer here is -1/12. All right. So that's going to be my final answer. I don't know if that was a multiple choice question, but it doesn't look like it. But that's how you handle that kind of question. All right, I'm going to spend a bit of time on quadratics. I'm going to go back to Algebra 2 because I know I've got a few Algebra 2 students here. I want to remind Algebra 2 students about things that we can do with graphing quadratics. What you want to know about quadratics is that there are really three ways that you could write any quadratic equation. Well, at least two, sometimes there are three. And one of the ways is this one, which is called standard form. This is standard. There's another, because it's ax squared plus bx plus c. There's another one that you're familiar with called the vertex form. Vertex quadratics look like this. A times x minus h squared plus k. And you know that that h and k is the vertex. You're welcome, Alexandra. The vertex is h comma k. Standard form, I'm going to write that out here. Right, standard form is ax is f of x is equal to ax squared plus bx plus c. The third form that I was referring to is the factored form. Some are not easy to factor. Some can't be factored with integers, but if they can, they would be written as a times x minus x1 times x minus x2, where x1 and x2 would be the x-intercepts for the quadratic. Up here, h comma k is the vertex. Over here, the only thing that we really know is that c is our y-intercept. But if your equation is in standard form, you can get the vertex by using this formula, negative b over 2a. That's a formula that only applies to the standard form for a quadratic, and it gives you the x coordinate for the vertex. If you want to get the y coordinate for the vertex, you plug that x value back into the function and get the y coordinate of the vertex. But one thing I want to point out to you, that the only thing that all three of these forms of quadratics have in common is they all have the same a. So if you know the leading coefficient in front of the x squared in standard form, it's the same number that has to be in the equivalent version factored form and in the vertex form, like that. So let's, and by the way, one of the things about converting to vertex form is it does help to graph, because you were learning in your Algebra 2 class how to graph things by how to graph quadratics and other functions by what we call transformation. And I think I might have some examples here. I don't know if I pulled them over or not that were in vertex form. But let's get one in vertex form. Let's do that. Let's take this, which is in standard form, and let's use the formula that I just showed you on how to get the x coordinate for the vertex. Negative b would be 6, a is 1, so the x coordinate is 3. Let's find f of 3. F of 3 is 9 minus 18 plus 8. I'm going with negative 1. So I know that the vertex is at 3, negative 1. Therefore, I could write the vertex form of this quadratic. F of x would be x minus 3 squared minus 1. And remember, whatever the coefficient is here in front of the x squared, it's the same coefficient that would be in front of those parentheses. So I'm not just ignoring the fact that I don't know what that value is, because I do know what it is. It matches the value up here. So your teachers will tell you that there's a technique for going from standard form into vertex form. It's called completing the square. And sure, completing the square is perfectly fine thing to know. You should know how to do it because it does at times will help you solve a quadratic equation without using the quadratic formula. However, if you have a function that's in standard form, I might argue that in many cases it can be easier to just find the vertex using negative b over 2a, and then you've got it in vertex form. And then if I wanted to graph that equation, here's why vertex form is so handy when it comes to graphing, because you know what the graph of y equals x squared looks like, or you should know. You should know where the vertex is and what the patterns are to get the other points on the curve. You know that the vertex here is 0, 0. And you also know that if you're to move away from the vertex and go right 1 unit, you would go up 1 unit to get to a point that would be on the parabola. If you go 2 units to the right of the vertex, you would go up 4 because 2 squared is 4. And right 3 means you would go up 3 squared or 9. But here, this vertex form is a transformed version of this. And so its vertex is at 3, -1. It's over here. And since the coefficient is 1, I know that I can do these moves to get the other points. Right 1, up 1. From the vertex, right 2, up 1, 2, 3, 4. Right 3, up 9. I also know that it is symmetrical across the axis of symmetry. And so I can plot these other points over here and connect those with a smooth curve, and you've got your parabola. Let me show you what happens when you have a coefficient other than 1 in front. Let's try one of those. Maybe this one. That's not the best one. Let's go back over here. Well, let's do it with the negative in front here. Yeah, let's try this one. If I want to convert that into vertex form, what I'm going to do is find the x coordinate of the vertex. I'm using -b over 2a. Negative b would be -8 over 2 times a -1. That's a +4. If I find f of 4, that's going to be a -16. Don't forget that minus gets applied after you square. It's not -x squared. So it's still a negative right here. So that's a common mistake. -16 plus 32 minus 17. That, my goodness, that would be 16 minus 17, right? So -1. So it looks like our vertex here is at 4, -1. I'm now ready to write this in vertex form. I'm going to put a -1 in front of the parentheses. There you go. Okay, much easier than using the method of completing the square, if you know how to use completing the square. And that's what we have there. Okay, students, looking for questions, but I don't see any. I'm going to go to one more question on calculus. Don't think we've done this one yet. That one was similar to the one we did before. That looks familiar. That's an equation of the tangent line for the inverse of f of x right there. Okay. Yeah, at x equals -2. So basically what they're wanting is for the inverse function, they want me to find the equation of the tangent line of the inverse at x equals -2. Got it. Well, what I'm going to do is realize that if x is equal to -2 on the inverse, it's equal to y in the regular f of x. So I'm going to plug the -2 in for y of the f of x function and see if there's a way we come up with the solution here. I will go ahead and take the 1 away to make things maybe a little bit easier and put a -3 over there. I think we know what this is going to be here. So -3, -2x cubed minus x. So what number would I plug in there? That's x equals 1, right? If x is a 1, I get -2 minus 1, -3. So that's 1. So that means then that -2, 1, -2 is a point on f of x. I think Alexandria had a little table here, which means that would be a 1. So 1, -2, -2, 1 on G. So this is going to be our point of tangency that we're going to use to build our tangent line equation. But I still need to get the slope of the tangent line. So what we have to do, since f and g, yeah, it's inverse. We're calling g the inverse function. Okay, so what I need to do still, though, is I need to get the derivative of the inverse function at -2. So that's going to be 1 over f prime at g of negative 2? Well, we determined finally what g of negative 2 was. G of negative 2 is 1. So therefore, that's 1 over f prime evaluated at 1. We need to take the derivative of f and evaluate it at 1. F prime of x is negative 6x squared minus 1. Therefore, f prime of 1 is a negative 7. Negative 6 minus 1. Negative 1/7. That's the slope of the tangent line. Or I should say, I almost made that mistake. It's 1 over negative 1. Hold on. Nope. I had that right. It's a 7. So it's going to be a negative 1/7 because it was negative 7. So it's negative 1/7. So now I have everything that I need. I have the point of tangency, which was negative 2, 1. We're talking about the inverse function. So it does touch at 2, negative 1, and it has a slope of negative 1/7. So the equation of that tangent line is going to be y plus 1, right? Y minus a negative 1 is equal to negative 1/7 times x minus 2, like that. And that should be the right answer there, Alexandria. I don't know if you got right answers there, but that looks like that's the one, or at least that's what I'm going with. You are welcome. And students, I guess that's it. I don't have a whole lot else for you unless you have a question. We can still go for a few more minutes if you want to type a question in or want me to address a topic that is causing you grief in your math class. Nothing? Well, I hope it was enlightening for you, and I hope it was helpful tonight. Hope we covered something along the way that maybe moves you further along in your math journey. Next week, I plan on being here again, so hopefully I'll see you here. Everybody stay safe with the storm that seems like it's going to be impacting our area, and stay safe, and I'll see you next time. Good night, everybody. Have a wonderful week. Bye now. All right, Noah, great, awesome. Glad to help.